same day. Like hydraulics test. Again.
Yeah, I talked to him.
And you're trying to tell us you didn't do that on purpose.
I didn't.
And you got both of them. The only two tests in this class are on the same day as the only two tests in this
I
class.
promise you in our faculty meeting, okay, let's see how we can make their lives a living hell.
That was the Virginia conference, that's why he
Yeah, I know. It'll be okay. We made it through this.
We'll figure something out. We have some things to discuss today.
Oh my.
What we're going to do is this. I want to get right into it. I'm passing the sign-in sheet around. Everybody, pay attention. Hi. What's up? All right. Here's what we're going to do. I'm going to get this example on compression steel not yielding done somewhat expeditiously, and then we'll talk about the celebration. So. Not bad, but we've got some decisions, so we'll talk about that then. I do have homework 4. I'm going to return that as well as the exam here in a little bit. I do want to get this example completed somewhat quickly so that you all are armed with everything that you need to finish homework 5. Okay, because homework 5 has 3 T-beam problems, but 1 doubly reinforced problem. We did the one where the compression steel yielded. Now we need to do one where the compression steel doesn't yield. It's fairly plug and chug, but I do want to go ahead and knock this out. So just so everybody remembers, this was the problem that we did last time. The problem, we had 2 number 9s on top, we had 4 number 11s on the bottom. We had all of our material properties here. Now the first thing that we did is we assumed that the compression steel yielded. Okay? And so we said, okay, let's use equilibrium to solve for A. C equals A over beta 1, and then we use that C value to compute our strains. And so this first strain computation, what we were doing was we were checking, okay, here's the strain in the steel, here's the strain at yielding. And since the strain was higher, what that meant, I heard the door open. What that meant was that our assumption was in fact valid. We assumed that the compression steel yielded. In fact, it did yield. Since we were in the habit of computing strains, we said, what the heck, let's just go ahead and figure out phi, computed our expression for equilibrium, and everything worked out that C equals T, developed our expression for Mn, and there you go. Okay? So that expression for Mn actually still works. The only thing that changes is that if your compression steel doesn't yield, this changes. Okay? So with that, I'm going to just hop right into our next problem. So I'm going to do this sort of the same way. The beam looks very, very similar. All I did was tweak a few quantities. So instead of 3 KSI concrete, we've got 4 KSI concrete. And instead of 2 number 9s, we have 2 number 7s, and I think I changed that to 4 number 10s. But by and large, this is a very typical doubly reinforced section. Now we're going to see what happens when the compression steel doesn't yield. Now we're still going to do the analysis assuming that it does yield, and then we're going to see what happens. So let me just get right into it. Let me get the lights adjusted. Okay, so here's the beam. So this is example 11B. All right. So again, we know that FC prime is 4 KSI instead of 3 KSI. Now that means still that beta 1 is 0.85. Again, anytime that FC prime is 4 KSI or lower, FC or beta 1 is 0.85. Next thing we know that we're dealing with grade 60 steel. So we then know, because of that, that our strain at yielding is 60 KSI over what? 29,000. And so I'm just going to go ahead and tell you that that's 0.00207, but by now we've done that calc a few times, so I feel like that's pretty straightforward. And we know that our limiting strain is that plus 0.003. So that's 0.00507. Okay? So here's that. Now again, what I'm going to do is the same thing I did last time. I'm going to assume that the compression steel in fact does yield. So over here, we're going to assume the compression steel yields. So C sub C plus CS prime is TS, or 0.85 FC prime AB plus AS prime FY is AS FY. And then this is the same, I mean, I know I'm going through this kind of quickly, but so far I'm literally doing the exact same thing I did in the last example. We set this up and then we recognize, well, what do we not know? We don't know A. You know, we know everything else about the beam. We know all the areas of the steels. We know B, we know D and D prime. We know the material properties again, so we just need to determine A. And so I'm going to do that by saying AS minus AS prime times FY, 0.85 FC prime B. So that's, now keep in mind, we're doing the same thing that we did in the last problem, but the values are different. So 5.09 minus 1.2 times 60 KSI, 0.85, 4 KSI, and then 14 inches. So, does anybody have that for me? What's that? I do too. I like to hear it. Everybody's prepared. Anybody got an answer for me?
4.93.
There you go.
That's interesting.
Yep. Second on that. Good stuff. Next, so remember, we made an assumption that the compression steel yielded. To verify that assumption, we need the strain in that steel. And in order to compute the strain, we need the distance C. So I want you to sort of think, it's like thinking backwards. I need the strain, so I need C. Compute C, I need A. So that's why we computed A first, then C, and then the strain. So C is A over beta 1, which is 4.903 divided by 0.85. And that equals what? There we go. 5.7. I think it was like 6.9.
Yeah.
And I assume I got 7 on it. Okay. So the next thing I'm going to do, now I'm going to compute the strain. Now I'm computing the strain in the upper layer of steel. So that's the epsilon sub S prime. And so that's 0.003. This is C minus D prime over C, right? I think that's the formula we used last time, right? So 0.003, and then, so 5.769 minus 2.5 inches over 5.769. And so what are we getting for a strain value here? Anybody got an answer for me? Say like 5 decimal places on this.
00170.
00170. Do I have a second on that? Okay. Now, let's remember, okay, so this is the strain at the top. This is, or the compression steel. This is the strain in the compression steel. The strain required to yield it is 0.00207. So, has the compression steel yielded? No, it has not. Okay? Now, what that means is this. I want everybody to be crystal clear as to what that means. What that means is that that assumption is wrong. Because that assumption is wrong, everything in this box is wrong. Okay? So, we're going to need to compute a whole new C. We're going to need to compute a whole new C sub C and C sub S. Everything in that box is wrong. Okay? In our last problem, what happened in the last problem was that assumption was correct. So if you go back here, we found in the last problem that assumption was correct. So we went ahead and just used that C value to figure out what phi is. We don't do that here because that C value is wrong. Make sense? Okay. Now, that means we have to, sort of start from scratch. Fortunately, a lot of the math has been done for us. So, let me make sure everybody's clear on this. Why did I start down here? Let me move this up here so I got a little bit more room. I don't know what happened there. Okay. So, what I'll say is assumption invalid. And if you want, you can put next to it that the strain at yield was 0.00207. So the assumption was invalid. Okay. So what we've got to do is we have to re-perform our analysis assuming that the compression steel doesn't yield. Okay, now I've made that job a little easier for you. If you go to the notes, we sort of derived that together last time, right? So if the compression steel yielded, then the force is AS times Fy. If the compression steel has not yielded, the force is the area times whatever the stress is. And what is the stress? E times the strain. And what is the strain? 0.003 times this, what we just computed, or the formula we just used. So what do? I set C equals T, I do a little bit of algebra, and I come up with the following equation. Okay? So this quadratic equation will allow you to solve for a new C value that recognizes that the compression steel does not yield. And while it looks nasty, it's pretty plug and chug. And you'll see that here in a second. So I was lazy, so I just copied this image. So here's the expression. So if you look at this, look at these brackets, right? I got a pile of junk times C squared plus another pile of junk times C plus another pile of junk equals 0, or in this case minus another pile of junk equals 0. So what do? Let's compute each of these piles of junk. So let's take the first one. You like my technical terms, piles of junk? So 0.85 FC prime beta 1 B. Now, one of the things I'll go ahead and tell you, and we'll have a discussion about this on the exam, but this is actually probably one of the areas where being consistent with units probably isn't going to trip you up a lot because it's all beam dimensions and stresses. It's already in kips and inches. But if you want, I'll be consistent just to make sure that everything follows appropriate units. 0.85 for KSI, 0.85, 14 inches. So everything is in kips and inches already, okay? So when I compute this out, does anybody have a number for me here? Yes.
40.46.
40.46, okay? Do you have a second on that? Okay, so let me sort of box that number. Okay, now let's do the second one. AS prime ES 0.003 minus ASFY equals, so 1.20 inches squared. What's ES?
29,000.
There we go, and we'll burn that number into the back of your head by the time you're done. 0.003 minus 5.09 inches squared, 60 KSI. So again, everything's already in kips and inches. So everything already matches. So tell me what you get here.
-201.
-201. So it comes out negative, right? That's probably the one thing that you've got to watch with this is that you track your signs, okay? So this comes out as -201. Do I have a second on that? Okay. Now, here's the way that I do this. The final term is AS prime ES 0.003 D prime. But if you notice in the equation, there's a negative here. So I go ahead and put the negative there. Okay? So this is negative. And that is negative 1.20 inches squared, 29,000 KSI, 0.003. D prime is 2.5 inches. And that equals what? So do I have an answer for this one?
261.
261, is it negative or positive?
Negative.
This is what I'm talking about. Keep track of the signs here, okay? This is negative 261. Everybody see what I'm doing here? So my quadratic expression is going to be the blue box 40.46 c squared, this blue box c, this blue box equals 0. So just keep track of it, okay? Does that make sense? Now if I solve this expression, I'm going to get two values for C1 or for C. And you should be able to do that in your Casio FX 115 ES pluses. But have an let's report each one. There's two of them.
6.04.
Give me one more decimal place on that one.
6.037.
Okay, the next one.
Negative 1.061.
Okay. Do I have a second on that? Okay. Now, what we're solving for, let's keep in mind what we're solving for is C, right? Remember what C is? You have your strain profile, and C is the distance from the very, very top of the beam to the point that's zero strain. So as a result, one of these answers doesn't make any sense. And which one is that? The negative one. So our C value in this case is going to be 6.037. okay? Now, I want to point out, this is different than that, okay? When we assumed that the compression steel yielded, we got a C value of 5.77 inches. That was wrong, okay? So you almost have got to think to yourself, okay, that value's gone. Gone. The new value is 6.037. And this value is the right value of C that maintains equilibrium, okay? And if you don't believe me, I'm going to show you here in a second. But is everybody with me so far? Okay. Now, like I said, again, this is the magic value of C that maintains equilibrium. Let's look at equilibrium. Now, what do I mean by equilibrium? I mean C equals T. So let's compute each of those forces. Let's start off with C for the concrete. Now the concrete compressive force is 0.85 FC prime AB, just like it has been, okay? Now, what's A? Exactly. It's not what we got up here. What we got up here was 4.903 inches. If you try and use 4.903 inches right here, bad. Okay, because that value is wrong. That value was based on an assumption that was invalid. A, remember, A is beta 1 times C. Okay, so what I'm going to do is I'm going to say 0.85 times 4 KSI, and then where it says A, I'm going to say 0.85 times 6.037. Oh, don't forget the B. Oops. Okay, does anybody have a value on that one for me? So if you want, maybe I'll put over here, note A equals beta 1 times C. Bless you. Anybody have a value? We can probably go with like 2 decimal places. 2's probably fine for what we're doing here.
5.13.
Say it again.
5.13.
5.13?
Oh, no, that was the A value, 17.45. Is it still wrong?
Hold on. I'm talking the whole thing.
244,
244.26 kips. All right, is that, everybody got that? Okay. And so you got that? Okay. Now, what about, so there's 2 compressive forces, right? There's the compressive force in the concrete, and then there's the compressive force in that upper layer of steel. Now, if you say that compressive force is the area times Fy, that's wrong, okay? That's wrong because that's assuming that the compression steel yields. It doesn't yield. It is, in fact, the area times whatever the stress is, which is E times the strain, which is that. So unfortunately, this term is a bit more, it's a bit more involved. All right, everybody with me on that? Now, let me just make sure that I'm keeping record of what we computed. So we have a C sub C of 244.26 kips. We have a CS prime, which we haven't done yet, and we've got a tensile force in the lower layer of steel. We've got to do that too. So let's chug this one out. So 1.2 inches squared, 29,000 KSI, 0.003, 6.037 inches minus 2.5 inches over 6.037 inches. And we'll say 2 decimal places.
.17 kips.
61.17 kips. Do I have a second on that? So this is 61.17 kips. Okay? Now, we've got one more force to compute. Let's compute the tensile force. So that is ASFY. So 5.09 square inches times 60 KSI. Let me put a little line here so I divide that. Very easy to see. So what is that? 300 something, right? 305.4? Do I have a second on that? Okay. Now help me out. What is the total compressive force?
305.96.
305.96?
I got 305.43.
I second that one.
I did 0.7, not 0.17.
So 305.4, 305.4. What's the difference? The difference is rounding. Because if you solved this out, this value probably went on forever. It's probably 6.037248, you know. And so if you were to track all that out, you would have gotten exactly 305.4 here and 305.4 there. You should do this for every doubly reinforced problem that you do to verify that C equals T. You did a lot of button pushing to get from the beginning of the problem to this point. So it's worth checking it, okay? It's worth checking. Sound good? So not only do we have our quantities, but we know that everything's right. So what we do from here on out is pretty straightforward. So we can still, we can still use our same expression for Mn, which is C sub C times D minus A over 2 plus C sub S prime D minus D prime. And so that is 244.26 kips times 24 minus, did we compute A? No, but we have beta 1C, right? So I'm just going to say 0.85 times 6.037 plus 61.17 kips times, and what's next, 24 minus 2.5 inches. And in order to just save us a little bit of time, I'll just go ahead and tell you that that comes out, when you plug and chug all of that, that comes out to be 6560.69. And then that's a moment, so the units are inch kips, and then converting to foot kips, you divide by 12, 545.89. And then the last thing that you do is you compute the strain in the lower layer of steel. So When you do that, you get 0.00893, and the reason that that we needed to do that is because we have to compare that against the limiting strain of 0.00507, and since it's larger, that means that phi is 0.9. So phi mn is that times that. Bless you. 491.3. While you all are sort of chugging that out, I'm going to hand back your homework 4. I've owed you that for a little while, and then after this, I think we're caught up on both classes on all of the homework. And really the one sort of, I guess, mistake worth mentioning on this homework was, on a lot of the problems, you came up with the design, but then you had to go through and verify said design. And a lot of you didn't do that. Like, we might not have done that in class, but that didn't mean you didn't have to do that on the homework. And that's, I think if there's any one issue, that was probably it. So yeah. So I'll give you all a sec to chug that out while I'm passing this around.